All right, good morning, everybody. We have two more lectures to do. Let me try to mute.
Good morning.
So today I want to go over the important slides, sort of having a quick final exam review. And then we will pick up where we left last time about the chemical reaction equilibrium and try to finish those discussions as well. And then this coming Thursday, we try to pick up a few problems and work together to illustrate how we are going to approach those problems, especially for the reaction equilibrium, and then we may review other type of problems this coming Thursday. So first of all, I've shared the two notes from previous years, and I was basically trying to go over all the interesting, important materials last year, for instance, with that class, and try to illustrate what would be the important things we need to cover. And I also want to remind you that I emailed the class of a list of 10 potential problems other than the reaction equilibrium, what could show up in the final exam. So again, I try to have 3 problems for the final exams, 2 hours, and some problems will be mainly testing on uh, the reading the application of the general concept, and some problem will involve the calculations like we saw from the exam 4. So here I want to first of all have a quick review of all the course materials and what is the plan uh, by the end of the semester, what we were trying to achieve, and now we can say that have we achieved those uh, ideas or not. So first of all, this is let me try to call my iPad. Maybe let's change the color. So this is a very general course description, as you can see. So we say that the course, what's going on? The general description is we try to cover the 3 laws of thermodynamics, and they are used in the analysis of phase equilibrium, uh, describing gas mixtures, liquid mixtures, and chemical reaction equilibrium. And we will also briefly cover power cycles and refrigerations. So there you can see that indeed the keywords we are looking at would be the 3 laws of thermodynamics. And then phase equilibrium, reaction equilibrium, uh, especially involving the gas and liquid mixtures, right? So we have 3 laws. We have mixtures, and we are going to have VLE, and then reaction equilibrium. So that is indeed the core part of thermal. If we come to this 2-sentence description. And then here I also want to share with you that this is a course assessment. So every teaching cycle, in the end of the semester, I need to put together a report, try to analyze the performance of the class, try to analyze which item we shall have more discussions in the coming year based on the class performance. So this is the list of 8 course assessment. As you can see that the best way to have the course assessment would be, number one is having the homework problems, right? Number two is try to have a problem in the exam so that we can better collect the statistics. So I want to quickly go over all those 8 items to see if we have already covered all those assessments. Number one is we need to formulate the material energy and entropy balance for the batch or steady state system. So this is basically a revisit of Mohi, trying to see that if we are able to set up the equation for our calculation. And as you can see that the steady state here is our main focus for the equation setup. And then the second item would be mainly focusing on the first and second law of thermodynamics. So if you cannot recall the three laws of thermodynamics, we need to go back and check what would be the statement of those laws. Okay, we need to understand and know how to apply the laws. The third item would be you need to find and calculate thermodynamic properties using table graph, correlations, and appropriate software. So this is, for instance, if you recall the steam table we have been using, if you recall the VLE diagram, and then we also discussed some other HS diagram, log P, entropy diagram we had in the previous lecture. Those would be the requirement for the thermodynamic property calculations. And for many numerical calculations, it's not uh, very easy to figure that out by hand calculation. So we'd better use the knowledge we learn from the uh, uh, computer class or numerical class to solve those calculations. Then the fourth item would be calculate chemical reaction equilibrium relationships. So that we have not covered, or we have not had the assessment. So this is one of the main part of our final exam for the reaction equilibrium to see if we have a decent understanding of that. Then the fifth would be calculate the fugacity and fugacity coefficient of gas components, activity and activity coefficients of liquid components in solution. So that is basically the log phi I log the activity coefficient. We did some tests in the previous exam, and it's indeed the core part of our discussions recently. Then the sixth item would be understand the performance characteristics of compressor, turbine, power, and refrigeration cycle. So that would be the exam 3. We covered that. If you recall, we call this as chapter 7 to 9, and we need to understand each of the unit coming out of Carnot's cycle. What would be the use of each unit, whether we need to assume the isentropic process or not, right? So there you need to combine the first and second law, uh, combine the understanding of the Carnot cycle, and then we need to calculate work, heat, efficiency, so on, right? So we have that covered as well. And then item 7 will be calculate compositions of phases in equilibrium, both for ideal and non-ideal systems. We should be able to read the phase diagrams and understand the concept of immiscibility and the existence of azeotropes. So azeotrope is x1, y1, right? So this is again about the specific requirement of the VLE, the phase diagram, and we are able to uh, analysis the some special cases over there. Number 8 would be calculate the PVT relationship for gases using various equation of state. So if you recall, that is also a huge part in the uh, second unit. We were trying to introduce the four energy equations, the four derivative of those equations. We try to have the maximal correlations. And also on top of that, we were talking about the ideal gas equation, the van der Waals equation of state, and other general cubic equations, including Vario, including the corresponding state principles. So we introduced two different types of corresponding state principles, 2 parameter, 3 parameter, thanks to pizza, right? So those would be the calculations. Now, if you recall, we are here on this slide trying to uh, cover all those items by this semester. Okay.
Okay.
So using the following slides, I wrote from last year. I want to quickly go over those items to see if you agree with me, if you are on the same page with the class. So I want to start with this slide. So in chemical engineering, we try to understand the mixtures, and we try to have a prediction about the phase and about the distribution of components. So we are able to utilize physics, chemistry. We're able to control their reactions or just physical separation. Uh, and then we want to see whether this is uh, controllable or not. And then on the other side, we want to estimate how much energy we shall import in order to drive that process. So this is why I believe this one single slide can tell thousands of words, where you can see that starting from mixture as the import, we try to understand the redistribution of the components. By components, we can understand that as elements. We are going to use the reactions to reorganize those elements from CO to CO2, from methane to generate water by the combustion reaction, so on, right? And the other is about the phase redistribution. So there we may want to have a more gas phase of a specific component so that later on we can achieve better kinetics, or we can achieve a desired reaction in nanoporous materials, say. Otherwise, if you are having a liquid or solid phase, then it's not easy to uh, have mobile component or mobile species. And then you just cannot excite those molecules and having reaction or separation purposes. So there we try to understand what would be the phase equilibrium from the starting mixture. And what we will be relying on would be temperature and pressure, right? So we always try to manipulate temperature and pressure, and that choice is based on the reality. Once you have the container, once you have the plant, once you have everything set up, then you don't want to modify those facility too much, but you want to really understand the condition, mainly temperature and pressure, to see how we would achieve those desired changes. So that is indeed the core part of everything in chemical engineering. And then coming to those handwritten notes, I was basically trying to recall. So if you recall, we have the most useful concept of chemical potential, of fugacity, and we understand that chemical potential is closely connected with Gibbs energy, and from Gibbs energy, we are able to call all the other uh, energy equations, right? This is one route to connect, and the other route is whether it's uh, vapor liquid equilibrium or chemical reaction equilibrium, we always have to satisfy the equilibrium requirement. That is the 3 equations we are having over there, or this set of 3 equations: temperature, pressure, and chemical potential. Of course, we will transit from chemical potential to fugacity uh, and fugacity coefficient calculations, right? On the other side, we also need to recognize that the Gibbs energy is a descriptor for both VLE and reaction equilibrium. So that is, if we are uh, having the discussion from scratch, we always want to go from the definition or convenient equation of Gibbs energy and try to derive a few useful equations. Okay. And here, as I as I mentioned that in reality, we always want to manipulate temperature and pressure, and we are going to understand the X value of those mixture components, whether through the phase separation or reaction design. So this is one other way to understand the very general concept. We have the starting mixture. We try to see how we are going to manipulate the temperature, pressure, and achieve the desired distribution of the species and their phases. So when you recall those discussions on VLE and the reaction equilibrium, we really have to understand the fugacity calculation. Uh, and in order to do the fugacity calculation, uh, we are converting this into two different routes. One is we want to go from Fi in the mixture. You see the liquid component. This is Fi in the vapor. So that is no mistake. We can always start with this equation. Then from there, we have this so-called favorite equation, right? For the liquid phase, so this is Xi, activity coefficient, uh, and then Pi set, right? On the right-hand side for the vapor, this is Yi, fugacity coefficient, P total, all right? So for the phase equilibrium, we always try to go from the golden equation, golden but not too useful. Uh, we try to convert that into those coefficient calculation. For the reaction equilibrium, though, we are going to have this capital K, which is a bridge. If you recall, on one side, this is defined as the product of those Fi component. I'm going to just put it over here. On the other side, this is related with delta G naught of the reaction with delta H naught, so on. And we are able to evaluate the temperature effect on the reaction constant, right? So this is a route uh, if you are working on the reaction equilibrium calculation. Okay, I connect various components over there, but if we follow the Gibbs energy as the useful descriptor, then naturally you need to recall what is that Gibbs energy. And by the way, what would be the other energy equations we were talking about over the semester? So there we are going to have the entropy, we are going to have the Helmholtz, and then internal energy is of course the core for the first law thermodynamics. Be comfortable with those four derivative, those equations, dg, dh, dA, and du, right? So there the concept is one, we need to look at their independent parameters. And then along that direction, you may recall the Gibbs-Fish rule. Two, we always want to convert the pulse function calculation into state. Right? Because we can take advantage of the fact that state function, the property does not depend on the exact evolution. As long as we know the initial and final, we know the answer. Three, we always want to express those energy equations on easy available measurements. So there we try to utilize Maxwell. If I have to use some ds term, say ds over dt, then we try to see if I can express that as a function of dv over dp, for instance, right? So we try to convert the entropy calculation into some other easy measurement. So that is also the general idea we have developed over the course. And now, if you try to recall the first part of discussion by looking at the energy, the internal energy calculation, I hope you recall a few things as well. Number one, and I think that is also very important to have, is how we define the sign of energy, right? So we always say if this is energy into the system, then this is a positive. I always compare that to your bank account. If you receive a deposit, that's always a positive impact to your saving. If I have to do work on the surrounding, I have to spend a budget on a textbook, then this is a negative impact on the uh, saving account, right? So this is the science definition, and the other is from this uh, energy conservation equation, which is basically the first law of thermal, then we shall be able to run lots of calculations instead of the steady state flow process. Uh, so if you recall the steady state flow process, there we need to understand what quantity does not change, right? Whether it's the mass or some flow rate or uh, whatever quantity we have to use and set up the equation upon. So that is for the first law and the steady state flow process. And of course, now if we further break down the energy calculation, in the end, it's always the work and heat, right? Heat, we can burn the fuel, we can mix the high temperature with low temperature stuff. Work, we would have PV work, right? We would have this shaft work utilizing engine, pump, or other equipment to do a mechanical work upon the system, or the system will output this mechanical work, say turbine, right? So that is the work calculation. So for PV work, we just need to follow the equation, right? That there is a negative uh, PDV, right? So work is negative negative PDV, right? So this is the first law. Second law introduces the entropy, and the entropy definition is a little bit strange. Pay attention that we have this uh, heat. Heat is a pulse function, so we use this data, small amount of heat, and we need to satisfy this is the reversible. So now talking about the reversible, we have those requirements, right? We have the isothermal, isobaric, isentropic, reversible, irreversible. Those would be the, the, the descriptions we have used to describe the change of a system. There we need to understand what is the definition of reversible and what kinds of examples you can come up with reversible processes. So we have practiced examples, say ice melting, right? So if we know the ice can be melted at any temperature, as long as you adjust the pressure accordingly, then we can have the ice melting at minus 50 degrees C, for example, or we could hold on to that ice until 10 degrees C. Uh, as long as you change the pressure at a high temperature, we are still having the ice phase. Uh, so then what's the difference between those cases versus the ice melting at 180 and 0 degrees C? So there we had some examples on the reversible. I hope that is uh, useful to understand the reversible and irreversible. And then moving along to the third law, that is basically a patch to the entropy definition. Recall that in thermal we are interested in two different values. Uh, the most important is always the change. Say this is the change of the Gibbs energy, right? This is the change of the entropy. Uh, but sometimes we are also interested in the exact value, right? What would be the Gibbs energy G1 at the initial condition? What is the entropy for the final of the system when you have the uh, temperature, pressure, and composition? So this is why we need to understand both the change and the exact value. So over here, third law is just a patch, so that we know that at absolute 0 Kelvin with a perfect crystal, the entropy we define that is 0. Okay, so that is the third law. And then if you think about the calculations, uh, we were basically having lots of fun, and I think this is a hugely important part for our civilization that is coming out of Carnot, and thanks to his and other pioneers, their study, that we know that heat engine is possible, and we should be able to select the working fluid to understand the maximum efficiency. So there we need to have the 4 units, uh, isothermal processes, isentropic, uh, so on. So there we need to calculate the 4 different units. So this is what we call this as a power cycle calculation or heat engine calculations, right? So there we have the two core materials to review. One is how we are going to connect the 4 units, right? So we are having this loop that is a heat engine. If I have the uh, reversible or the refrigerator, then what would be the cycle? And over there, if I'm having those 4 units, what would be their individual uh, energy balance? What would be the work and the heat, right? And what would be the total? And based on that, how do we define the efficiency, right? And also, if you recall, we also have quite interesting discussion starting from the Carnot cycle, which is the Carnot cycle efficiency does not change when you are moving from ideal gas, imaginary gas phase to the real liquid system, for example. So that is also a very useful hint for the following discussion, and that's actually the reason why we we depend quite a lot on steam calculation uh, in the thermodynamics data, right? I also explained that one reason is that we are supposed to have lots of water to utilize in the industry, and number two is water itself uh, can drive lots of processes, whether for the uh, phase separations or for the reaction. So that is quite convenient for us to utilize, and it's very cheap. So there, that is somehow explaining why we have the uh, so much data reported in the appendix about steam. If you recall, that's saturated, superheated, uh, and we have other quantities, heat capacity, for example, for water. We have sort of a very good understanding of all the water properties at a macroscopic scale. And then talking about the thermodynamic data, I also list the diagram. I hope you can try to ask yourself whether you are happy with the PVT. The How about if I give you the HS diagram, so-called model diagram? Are you able to look up the quantities we are interested in? And we also have this log pressure versus enthalpy diagram, right? So those would be very useful diagram in both thermal and in the industry as well. So the other part is the equation of state, and we started that discussion once we finish those very general discussion of the three laws of the power cycle calculation. Uh, there we know that, hey, I can use just the gas phase to drive the Carnot cycle, for instance. Uh, and then from there, for the gas phase, how do I describe the gas phase? We need to have some correlation, have some equations to describe it. So there we start off by looking at the ideal gas equation, PV equals RT. And then, of course, we know that lots of gases are not uh, behaving perfectly according to the ideal gas equation. There we need to account for some deviation. And those would be the discussion of the uh, two other quantities we introduce into the equation. What is A? What is B? What kind of quantity they try to account for? And then moving forward with the help of Van der Waals equation, we were looking at other type of cubic equation of state, right? So there we have the Redditch-Kwong, we have RK, and other complicated equations. And there, I hope you recall we need to also understand the two different set of values. The most important is the critical condition, right? So we have TC, we have PC, we have VC, and then out of uh, the critical conditions, we are able to use the so-called reduced unit, PR, TR, PR, and VR, which is basically, if I look at TR, then this is the temperature of interest over its own critical temperature. And along that direction, we are able to be very lazy, smartly lazy. We say, hey, I have the so-called corresponding state principle, corresponding state uh, theory. That is, if I have two different molecules and they are same kind of group, say nitrogen and oxygen. If I don't look at their reactivity, then for the gas, they behave very much the same. Then I can say that if I have had the understanding of nitrogen, then I can uh, use that understanding to describe oxygen. That is through the reduced unit and the corresponding state principle. And of course, there we started introducing the intermolecular interactions, say hydrogen bond and complex contribution from uh, other feature of the system. Then we need to have the extension. It's no longer the two parameter, but we need to have the three parameter. Where is my three parameter? Yes, we need to have those omega value, and we typically follow PISA, his equation to understand the corresponding state principle, right? So those would be the discussions on the equation of state. And then on the other side, we utilize Taylor series expansion quite a few times, at least three times. One is when we are looking at the Taylor series expansion, trying to have the variable equation of state. The other time is we try to have the Henry's law, right? So those would be how we are going to connect everything into one single piece. And then very slow, then I hope you recall that we can we can pick up the density or volume as the descriptor in the equation, or we can pick up the pressure. And if that is the case, then we are going to have the so-called B, C, D, one set of coefficients, the other set of B prime, C prime, D prime, and we have equations to connect the two different sets. So that was also discussed previously in the lecture. And here, as I mentioned, we try to understand and make us comfortable what is the so-called isothermal process, adiabatic, reversible, right? And even state and pulse function. State function is much preferred in the calculation. Okay. So we've discussed a lot already. There's a small piece from chapter 4, and that is a quite annoying part of our calculation. But I hope you see that now that part is also quite critical uh, for both VLE and reaction. This is because, above all, if we want to drive the system, if we try to control the system, the quite effective way for us to do is we just try to manipulate the energy flow, right? So by the energy flow, then we can easily heat up a system, or we try to cool something off from the high temperature to a lower one, right? So no matter how you are going to do lots of uh, work on the energy flow manipulations. So this is why we need to look at how I'm going to achieve the Q, the energy flow of the system. So there we were mainly looking at the CP, CV, uh, and I hope you recall that we have the equation CP minus CV would be R. But we have some condition in order to have that equation, right? Go back and check what is the requirement in order to set up this equation. And then we also have the, like I have over there, we try to express the specific heat, try to understand its dependence on temperature. And we had this in the exam, and I hope the hint is strong enough that for those calculations, so basically we need to look at the two lengthy equations. And if possible, let's try to use Excel spreadsheet for those calculations. Otherwise, you can still achieve by looking up those coefficients to that CP equation, and then carefully putting them together for the calculation, right? So this is the chapter 4. And along the way, I think this might be the first place that we have the feeling that the temperature calculation is usually a little bit more challenging, which is if I need to figure out what the temperature is, I need to run the iteration. Uh, that is true here and true also later on for the VLE calculations, right? Are you guys able to recall those stuff while I talk, or completely blank?
Not completely blank.
It's coming back slowly.
Great.
A little overwhelming.
That's a good word for it.
Yeah, yeah. Well, this is why we need to spend some time to review for the final exam, right? But I just want to show you that probably without your notice, we've actually covered lots of materials, and you should have those pieces inside you. It's just somewhere in your mind. Okay. So now moving forward, well, we have a quite a nice discussion and quite a strong foundation of all those concepts: energy, work, calculation, the heat engine, power cycle, try to manipulate CP/CV and so on. And the next natural step is now they try to move from the ideal gas, right? We started with ideal gas. What if this is real gas? We've answered that question by equation of state. What if it's not the gas? I'm having some mixture, or I purposely want to have a liquid. Then what's the deal? So there we started with those discussions on mixtures, right? So along that direction, with the increasing number of quantities that we shall be able to manipulate, we need to come up with a plan. That plan is how many independent parameters we need to control in order to 100% determine the system. And that is actually super duper important in reality. And we actually have the tool through the Gibbs phase rule. So that is when you look at your system, 3 components, 4 components, you may have liquid phase, or liquid solid and vapor, whatever complicated phase you are going to have. That's not a big deal. Let's go back and follow the Gibbs phase rule to determine how many independent parameter I'm going to have. And then once I figure that out, I'm going to express everything, all the properties we're interested in. So later on, we realize that we have 6 quantities we need to understand, which is internal energy, enthalpy, Helmholtz, Gibbs, and very often we are interested in the volume. We are interested in the entropy, right? Volume, because well, we tend to put the temperature and pressure as control parameter. And then the other stuff would be the composition, or Ni, right? So there, once you figure out what kind of mixtures you have, then you pick up how many independent parameters you are going to manipulate. So I hope that's a quite logical flow. Now we move from ideal gas. Ideal gas, because Carnot cycle tells us that the fluid does not matter, but in reality, it does matter. We don't have that ideal gas ever in reality. So moving from real gas, and gas is not easy for most time. It's not easy to transport. So there we have the, quite reasonable requirement. How about liquid and solid? So this is why we need to realize, hey, gosh, I need to also understand the mixture. So now, if you think about the mixtures, then we are going to have gas phase mixtures, liquid phase mixtures. That would be the also simplified cases. But even for that 2 cases, we need to calculate, and we need to understand, for example, what is the deviation from the ideal gas? What is the deviation from ideal solution, right? So there we were looking at residual property and excess property calculations. This is number 1. Number 2, how do we separate the mixture into their pure components, right? If I have water as a liquid, sodium chloride as a solid, and I'm going to make a solution, then of course I'm physically having the mixing process. So there we are having the mixing process, or mixing property. All right, we devoted one whole chapter on those mixing property calculation, and I hope you somehow recall that. We try to connect that with the partial molar property. Okay, So there you probably need to also visit the previous slides if you cannot connect those components together. So this is the one route in terms of the big picture, why we are moving from ideal gas to real gas to mixtures to any other realistic systems. On the other route, then we still need to come up with a descriptor, right? You may say that, well, I have the Gibbs energy as you tell us up front. Yes, but Gibbs energy is not too easy to measure. What we are capable of measure would be temperature pressure composition, right? This is one reason that knowing Gibbs energy is a descriptor is not enough. The other reason is now we've spent so much time and we have a very good understanding of the ideal gas. I always want to take advantage of the understanding, try to see the deviation, try to make a approximation that maybe the temperature, the pressure is not terribly high, so maybe we can assume the ideal gas. So this is why in the following discussion, we always refer the ideal gas as a very good comparison. And this is indeed how we derive the fugacity with the help of Lewis, right? So the fugacity equation is not derived, is actually just following the natural understanding of ideal gas, and by comparing the ideal gas equation, we say, well, for real gas, for real liquid, for solids, uh, let's try to come up with a similar equation uh, for the ideal gas. So there we have this chemical potential is RTD log Fi. Okay. Or in other way, I can turn that into more like a definition type of discussion, right? So now moving forward, I hope the those discussions will be still uh, uh, flash in your memory. Say this is a mixing process, a partial mixing process, partial molar property discussion, and then moving forward, we are having the uh, two different chapters. One is specifically looking for the fugacity coefficient calculation. Right, we have TPX, TVX, equation of state, or using the table to run the calculations. On the other side, we are having the liquid, and we are looking at the activity coefficient. There we have lots of models, uh, Marguerite, Van Laar, Wilson, NRTL, and so on, right? So those will be the discussions, and I hope that at some point, you realize that the reference and the standard state is still very critical. This is because our definition simply tells us that d mu I is RT d log Fi. And I need to run the integration if I want to know at current state. I'm not interested only in the change, but also in the exact value. So if this is the case, then I need to find the initial and final, right? So over there, I also need to simulate the initial and final. So talking about the initial, then we were talking about the very natural choice would be the standard state. And there the standard state definition is any temperature. That would be any temperature, but the pressure has to be 1 bar, according to IUPAC definition of standard state, right? In reality, we are having a special standard state. Thanks to the textbook, we have this 298 Kelvin have lots of data from the appendix. And then P is 1 bar, right? But I want to point out that we are not limited in that two choices. If you are having low pressure, then we have our best friend, ideal gas. If you recall, we had exam problems on fugacity or chemical potential calculations from the steam table. We always look for the lowest pressure, right? 1 kPa as the actual value from the steam table. Lower enough, then everything will be simplified as the ideal gas, then the Fi at this P is 1 kPa is indeed 1 kPa itself, because that's the ideal gas. Fugacity is same as a partial pressure. Right, so those would be the small things. I hope by looking at the slides, someone said it's too much, but I would argue that in order to understand the big picture of thermal, you have to put all those together, complete the puzzle, and move on. Otherwise, you may survive in thermal, but you are going to have another nightmare in separation, in kinetics, or later on in transport. Later
Gotcha.
when you are in the graduate school, then all those things will bother you if you let them go at this time. Okay, all right. Moving forward, I hope it's not too surprising that we are having all those discussions about coefficients, about those various symbols, and for the Fi we don't have that, but we generally have the other hat. This is the partial molar property of component I. Right, so we have two different hats, and we have also two different. What is that? What is this symbol?
The initial state of a fugacity coefficient with
The standard initial state.
with extra standards because there's extra. All right.
That is actually the correct answer. So that is the standard state. This one is just to remind us that I'm looking at some initial value. So after that, coming back to the Gibbs engine, now we've manipulated all those equations. Now we know that the Gibbs integer, we can move on and express that as VdP SdT, the summation of chemical potential with respect to each component, mu I dmi. Now I know that when we are looking at the phase and reaction, it's always at the fixed temperature and pressure, then it's quite convenient for us to get rid of the first two terms, right? And there we can see that for the phase, then it's basically the chemical potential calculation, because we are going to measure those terms. For the reaction, I hope you realize that we have the other equation, which is what? Mu I dni. We are going to write that as a reaction coordinate, right? We are going to replace that by the reaction coordinate and move on. And that is the most recent discussions on the reaction equilibrium, right? So for the For the following slides, I'm going to leave those slides to you, and you can go back after our discussions on the reaction equilibrium to see if it's making sense to you, right? And then I also have I put together roughly about 100 slides, nothing special, nothing new. It's basically coming out of all the previous lectures. I was trying to put together those slides so you can quickly check your own understanding over there. So I would suggest that start with the review slides, and I have the other note, purely handwriting notes. Try to see if you are with me on those big picture discussions. And then talking about the final exam, how to review for the final exam, I would suggest that if you are not happy with certain concept, start with the short summary video. As I mentioned, sometimes they are not short, sometimes they are also 15 minutes, 20 minutes, but at least that is a condensed summary of important discussions for each topic. And I usually also suggest some important equation to look for those topics. And then homework and all the exams will be still extremely useful. And it looks like I always lose argument, and many of you think homework is optional. That is a terrible mistake. I try to emphasize that in future years, but homework is the only official practice we have. And if you lose that opportunity, then number one, you're going to spend much more time looking for proper materials during the exam. Number two, you don't realize that I have exam problems from the textbook examples or chapter problems very similar to your solved homework assignments. So that is quite sad on my side, but I just leave this to you for your future studies, and hopefully you change your attitude towards the homework assignments for other classes. So I believe that is my general tip for the final exam. And remember that the core part will be the reaction equilibrium, and I will pick up two other problems and revisit on the important concepts as we discussed here. So I'm going to leave those to you. Then if we could come back to the other set of slides, let me say done. Try to have the. So now if we come back, now let's switch the gear and try to look at specific reaction equilibrium. Right? You ready? Okay.
No, let's get it. Let's do it. Let's do it.
Okay.
Capital Pi.
Thank you, Connor. You're always very optimistic like me. You might be the second optimistic person in thermal. All right. Oh, why I'm doing this to you guys? So previously we were talking about the reaction. So let's still have the 2-minute recall. So that is the reaction. Once I have the reaction, there are many interested properties we need to look for. First is the stoichiometry values. Quickly, we have this nu total, nu of the reaction. Moving on, we are going to have each component, DMI, how I'm going to express this as a function of the reaction. Reaction coordinate, so that I'm going to have those yi values. Right. Number two, we need to also pay attention on those state. whether A is a gas phase, B is a liquid phase, C is a solid phase, D is a vapor phase. We need to keep that in mind because very quickly we are going to use the state to simplify our understanding. Number three, we are having those species. We are having those A, B, C, D reactants, products. We need to quickly recall that we are able to receive the delta G naught of the reaction, delta H naught of the reaction, okay, from the appendix. And if needed with a higher temperature, then we need chapter 4 to jump in and figure out what would be the effect. Now we are going to have delta H or delta G at high temperature, delta H at high temperature. Okay. How about pressure? We say pressure is not important for capital K. Okay. So the troublemaker is always high temperature over here. Okay. So this is why we need to figure out K, looking at all those. And now if you come back to the K definition, we define K as this, right? So we spend half of the time calculating K. And then we spend the other half of time to recall those fugacity calculations. So that is the essential of reaction equilibrium. So now if we move back, and this is basically again the slides we were talking about last time, revisiting the equations from chapter 4 and how to help us to calculate that capital K reaction constant. Okay, and then we were talking about that we are able to simplify for the gas phase. If you recall, we were trying to go from this equation, then we are looking at ideal gas or low pressure gas, high pressure, high temperature, high pressure, real gas, right? Or if you have any other reference on those, how do you calculate? So there we were also thinking about if this is the vapor phase, then very likely I need to evaluate, no, not this one. Right? We were talking about, in reality, to be exact, this shall be the mixture. But how we are going to figure out this is the pure component. And very often, if you recall, we said the gas phase molecule, they have to stay away from each other. So they are not going to affect each other's behavior too much. So this is why we typically always use the second expression over there. Okay, and over there you need to analyze, or looking at the problem statement hint, whether it's low pressure, then quickly you're going to get rid of that. If this is low pressure vapor phase, then this is YIP total, right? And YI is a function of epsilon. P total, typically it's known. So that essentially you're going to solve the equation. K is some value of yi, or moving forward, K is some equation of the reaction equilibrium, and problem solved. K is from the other part of the calculation. Okay. If you still feel confused, then my understanding is you have not finished reading all those examples, chapter examples in the reaction equilibrium. Otherwise, you would clearly see what is the pattern of this type of problems. So now, how about liquid phase reaction? Liquid phase reaction would be very similar to the gas phase. It might be a little bit more challenging because for the vapor phase, we can always utilize the low pressure ideal gas to quickly get rid of the standard state. For the liquid, we may have to calculate both, right? So now let's move on to look at the liquid phase reaction. So I hope this is still very clear to the class that again, this Fi of the naught is the fugacity of the pure component I at the temperature of the system. And the pressure is 1 bar according to the IUPAC standard state definition, right? And then number 2 is for the Fi with the head in the mixture, you can always convert that into Xi, activity coefficient, and Fi. You may recall that why, how about this? Do we have that? Not really. This is because thanks to those model development, if you recall, all the models, all the activity models we were talking about, we are able to describe complicated liquid molecular interactions. But in the end, we always try to set up a model that we can treat those individually as components, right? So when we talk about activity coefficient model, we always look at the component. And of course, those components will have their corresponding, when you are looking at those, I believe those are still ABC kind of coefficients. So the intermolecular interactions will be included in those coefficients. Okay, we do have to take care of the interactions of non-ideal solution, but not by the head, but by figuring out those coefficients in the activity coefficient models. And also, this equation is super duper useful. And I hope you can recall that when we talk about the activity, fugacity calculation, we were spending the majority of time on gas phases, but we did visit liquid phase for 2 cases. One is the low pressure liquid. We say this is basically the saturation pressure calculation, right? Antonio's equation is involved. The second is we have this correction. We have this Pauling correction factor, and recall that in the slides, I had one example of, I believe is water or some alcohol. When you increase the pressure, at some point you are going to see a big effect on the fugacity. So that is indeed the equation we had from the discussion over there. So there you can see that now if we try to look at that, then all the previous discussions will be helpful in the liquid-liquid reactions, right? So we are basically converting the ratio into the expression of the activity coefficient of the composition change, and then that's the exponential term, right? We just need to figure out PVT of the system. So this is how, in reality, we try to simplify from this very general equation for the liquid phase. So instead of simplifying each term, try to put this together using the liquid-liquid viscosity calculation equation from the previous, and try to discuss over here how we are going to simplify. And I have this very general expression will hold even at high pressure. So that is indeed the discussion of the Pauling factor, Pauling correction factor, right? So if for the exact calculation, then you just need to go for this. Okay. Moving from the equation to this one, so there we simply try to separate those easy measurable quantity to one side and the other to the other side, right? So here, K value we've figured out. So keep that in mind. Capital K, and the reaction coordinate. There are two parts of any of the reaction equilibrium problem. You always have to figure out capital K utilizing other data. And then you are going to set up the equation between capital K and reaction equilibrium epsilon, and eventually solve for this epsilon.
Is finding K in a liquid system the same as finding K in a gas system using the big delta G equation with the heat capacities?
Yes, exactly saying. When you look for the appendix of those heat of formation, then we even have solid. What would be the heat of formation for those components? For example, for water, you have data for both liquid and vapor. I forgot to check whether ice is also available, but that's a basic knowledge. The answer is yes. For the capital K calculation, we disregard the phase. Vapor, liquid, solid, they are using the same formula to calculate. Right? So then it's still the same kind of discussion. We have the understanding that if it's the moderate, and of course this is a relative term, right? Relative term means in reality, it's always good to have some estimation compared with having nothing, right? So if you are working on a brand new system without too much data from the literature, then you can start with the assumption that this is a moderate pressure, and you try to measure what would be the reaction equilibrium, and then compare that with the actual measurement of the reaction, and to improve from there. So that is also we discussed that in the viscosity calculation. If that is a moderate pressure, then this exponential term is very close to 1. So that is why on the right-hand side, we are going to have capital K. Okay. So now the equation would be, I have the xi, I have the activity coefficient. This is still the stoichiometry for each component. Then you are going to have the equation simplified over there. And if you happen to have a liquid system with quite similar liquid molecules, then you can say that I can assume this is the ideal solution. If this is the ideal solution, then those activity coefficient would be 1. So there, it's very similar to the moderate pressure for gas phases. So there, I'm going to essentially convert that into the calculation of K and Xi. Xi is a composition. And recall that we are always required in the reaction equilibrium calculation, figure out what would be the xi expression as the reaction equilibrium. If you recall, we have this, say xi would be n naught of the total, the initial of the total, right? Then I'm going to have what? Nu, this is not V, that's nu. That's okay. Reaction equilibrium, right? Over Ni over the initial plus nu I. Okay. So those new value would be available to us if I know the reaction. And then those would be the initial setup of the reacting system. So eventually you're going to see that this is only involving epsilon as the unknown quantity in the equation. All right. So I just want to quickly remind you that you still owe me the reading and the exercise by yourself on those examples. Like this example, I believe this is also from the textbook and the list I suggested in the previous email. You have to make sure you are comfortable on those, all right?
All right.
And I want to stop here so that this coming Thursday, I will try to have 3 to 4 examples, not only for the reaction equilibrium part, but other parts as well. And then we have some practice together.
Killer.
Right. Stop recording.